In this video, I'm going to go over a few problems in each of the chapters 5, 6, and 7. Let's begin with this problem in chapter 5, which was a chapter on gas laws. The pressure inside a hydrogen gas cylinder was 2.1 atmospheres at 21 degrees Celsius. What is the pressure if the temperature increases to 99 degrees Celsius? Let's assume the quantity, number of moles, and volume does not change. With any gas law problem, the easiest way, I believe, to decide which equation to use is to start with the ideal gas law, which is easy to remember, PV equals nRT, and then determine which, if any, of the variables are constant. In that particular problem, it stated that the volume and the number of moles did not change. So you have delta V equals 0, delta N equals 0. If you look at the bottom right-hand corner, where I state that delta V and delta N both equal 0, that means they're constant, no change. We can apply Gay-Lussac's law, which states that the pressure over volume in one situation equals the pressure over volume in the second situation. So let's go back to our problem and solve it. The important thing in this particular problem to remember is that all temperatures must be converted to Kelvin in order to get the correct answers. If you don't convert to Kelvin from Celsius, you'll miss the answer. We rearranged P1 T1 equals P2 T2 to solve for T2. And when I plug in the values for pressure, convert the temperatures T1 to Kelvin and T2 to Kelvin, I can solve for the final pressure, and that turns out to be 2.66 atmospheres. Let's look at this next problem. It asks the question, what is the temperature of 0.40 moles of gas at a pressure of 1.5 atmospheres and a volume of 11.6 liters? Now, we're not asking to determine what the temperature is from one situation to another, or what the volume is from one to the other, or what the pressure is at P1 versus P2. This is like a question having a snapshot in time, where you simply need to apply the ideal gas law, PV equals nRT, rearranging the equation and solving for T. When you rearrange the ideal gas law to solve for T, you get PV over nR. Plug in the variables, pressure in atmosphere, volume in liters, moles is a number. And if so, you can use the gas constant 0.0821 because it has units of atmospheres, liters, moles, K. And when you solve that problem, you get a temperature of 530 K, 530 Kelvin. The next problem I'd like to go over in that gas laws chapter is a stoichiometry problem. Let's look at this reaction between acetylene and oxygen. We produce carbon dioxide and water. As in any stoichiometry problem, you want to always make sure you have a balanced equation. Hence, I have coefficients of 2 and 5 and 4 and 2 in it to obey laws of conservation of mass. So here's the question. What is the pressure in atmosphere of CO2 if the temperature equals 25 degrees Celsius and the volume equals 5.0 liters? Starting with 100 grams of acetylene, C2H2. Well, first part, in Roman numeral number 1, I'm going to do a mass-to-mass stoichiometry problem, converting 100 grams of C2H2 into the number of moles of CO2 that I will produce. And it's not 3 steps because I don't need to determine the mass of CO2, I just want the number of moles. So it's a 2-step problem. First, I take 100 grams of C2H2, divide it by the molar mass of C2H2, which is 26 grams per mole, and then I multiply it by the mole ratio. There's 4 moles of CO2 for every 2 moles of C2H2. And when I do that, the calculation comes out to be 7.69 moles of CO2. So now I have the number of moles of CO2, or N. I can then apply that number with the other variables of temperature and volume into the ideal gas law equation and solve for pressure. As always, we have to make sure we use in the calculation temperature and Kelvin. So when I plug in to solve for pressure, P is equal to nRT over V, I get P equals 7.69 moles times the ideal gas constant of 0.0821 times the temperature in Kelvin divided by the volume in liters. And the answer comes out to be 37.6 atmospheres. Now I'd like to go over a couple of problems in Chapter 6, the chapter on thermochemistry. Early in that chapter, we discussed the concept of internal energy. The change in internal energy between the systems and surroundings is equal to Q plus W, or heat plus work. What signs of Q and W will I obtain if I have work done on the surroundings by the system and heat is lost to the surroundings by the system? Let's talk about Q first, that's heat. If you have an exothermic reaction, as we have in this example, heat is lost to the surroundings by the system. Q is going to be negative. Work, you have work is done on the surroundings by the system. That means work is also negative. Work is positive when you have surroundings doing work on the system. So my answer is Q will be negative, W will be negative. The overall change in energy, therefore, must be negative. Let's look at another problem in the thermochemistry chapter. Here's a reaction. Fe2O3 plus carbon monoxide produces Fe3O4 plus carbon dioxide. What is the overall change in enthalpy of reaction for this reaction if you're given the individual heats of formation for the individual substances listed in the left side in units of kilojoules per mole? If you have known values of the change in enthalpy of formation for different substances, you can calculate what they will come to for the overall change in enthalpy for the reaction using this equation. The sum of the enthalpy of formations of the products minus the enthalpy of formation for the reactants equals that for the reaction. Now keep in mind your values, your units are in kilojoules per mole. So you need to take into account the balanced equation with the stoichiometric coefficients. When you do that, I want to adjust the view so we can see the entire reaction and the results. As I said, the heat of change in enthalpy of reaction is equal to the sum of the enthalpy of formations of the products minus that of the reactants. The products are 2 moles of the value of Fe3O4 plus the 1 mole times the value of CO2. In these kind of problems, watch your signs. You have to be careful that you are using pluses and minuses correctly. That's one product minus the heat of formation of CO2, which is 3 moles times, which is 1 mole times minus 394 kilojoules per mole. From all of that sum of the products, we subtract the sum of the reactants, which is 3 moles times minus 824 for Fe2O3, plus 1 mole times minus 111 for carbon monoxide. You add up correctly, again, watch your signs, and you get a value of minus 47 kilojoules. Try this, stop your recording and try this yourself and make sure you get the same answer. The next problem I'd like to go over from chapter 6, the chapter on thermochemistry, is an application of Hess's law. Let's say you're given change in enthalpy reactions for these 2 reactions. The first one is SO2 yields sulfur plus O2 with a delta H of reaction, standard of enthalpy change for reaction of positive 296.8 kilojoules. And the second given piece of data is SO2 plus O2 yields SO3. Or to be exact, 2 SO2 plus O2 yields 2 SO3. That is a change in enthalpy of reaction of minus 197.8 kilojoules. Let's use that information given to us and find the delta H for reaction for the reaction at the bottom. 4 sulfur trioxides yielding 4 sulfur and 6 oxygen gas molecules. To use the information above and to find the change in enthalpy for of reaction for that new equation, we're going to first reverse the second given value above and multiply it by 2. So if you reverse that equation of the data given to us at the top, equation number 2, and multiply it by 2, I will get 4 sulfur trioxides, yield 4 sulfur dioxides, and 2 O2 gas. Reverse the sign and multiply by 2, I get a positive 395.6 kilojoules from that part. Then I'm going to take the first reaction, SO2 yields S and O2, and multiply it by 4. So it becomes 4 SO2, 4S, yields 4 S's and 4 O2s, and the delta H of reaction, the standard enthalpy change of reaction for that is 4 times that, 4 times 296.8, or 1,187.2. Now, if you add up those two new equations, you'll see that the 4 SO2s cancel from the top reaction and the bottom reaction. And the sum of those two reactions is 4 SO3 yields 4S plus 6 O2. That's exactly what we're looking for. Therefore, the sum of the two enthalpy changes of reaction equals 1,583 kilojoules. Try this again. Try this one yourself. Stop the video and see if you get the same answer. Lastly, we're going to talk about a few problems in Chapter 7, the quantum mechanical model of the atom. Early in the chapter, it states that this symbol here is new. It stands for frequency in units of reciprocal seconds. Lambda equals wavelength. Typically, when measured in units of nanometers, but in many problems you'll see units of meters. So you need to know the conversion of nanometers to meters. 1 meter equals 1 times 10 to the minus 9 nanometers. That's wavelength. So that's inversely proportional of frequency to wavelength. It turns out that the frequency times the wavelength equals c, which is the speed of light, which we'll use a value of 3.0 times 10 to the 9 meters per second. So let's solve this question. If you're given a wavelength of a particular spectrum, what is the frequency? We're going to use the equation here to rearrange and solve for frequency, which is nu. Nu is equal to the speed of light divided by the wavelength. The only trick to this kind of problem is to make sure if you represent speed of light as 3 times 10 to the 8 meters per second, we have to represent wavelength in meters as well. 488 nanometers becomes 488 times 10 to the minus 9 meters. When you do the math, you get 6.14 times 10 to the minus 14 reciprocal seconds. The last type of problem I'd like to go over in Chapter 7 is quantum numbers. You should know what the 4 quantum numbers stand for. N, L, M sub L, and M sub S. Also, you should be able to identify the unique 4 quantum numbers for each electron representing all the elements in the periodic table. So let's do this by answering a couple of broad questions. Let's identify all the possible quantum numbers that exist for the 3p orbital, for any of the 6 3p orbitals. I'm going to use this nice periodic table that shows all the different quantum numbers and the various possibilities. It's attached to the audio lecture I provide for this chapter. So we're looking for all the different possible sets of quantum numbers for any electron that exists in the 3p energy level. Where here's energy level 3, starting with sodium. 3p, it starts with aluminum. It goes to 18, which is argon. So the 3p electrons, there's 1, 2, 3, 4, 5, 6. So we ought to be able to come up with 6 sets of 4 different quantum numbers. Well, of course, they will all begin with a primary quantum number starting with 3. And they will all have the same L quantum number of 1. So they should all be 3, 1. But M sub L can have 6 possibilities. Actually, let me back up. M sub L can only have 3 possibilities. M sub L is going to have values of plus L to minus L. If L equals 1, those values are minus 1, 0, and plus 1. Each of those values of M sub L can have plus or minus M sub S, the spin quantum numbers. So one set of quantum numbers for the 6 electrons in the 3p level are 3, 1, minus 1, plus 1/2. Another one is 3, 1, minus 1, minus 1/2. The next one would be 3, 1, 0, plus 1/2. Next one, 3, 1, 0, minus 1/2. And the last two would be 3, 1, plus 1, plus 1/2, or 3, 1, plus 1, minus 1/2. Next, let's come up with the unique set of 4 quantum numbers for all the possibilities of the 4d orbital. Going back to this periodic table that I attached it to the audio lecture of this chapter, you can see 4d will exist right here. We know the first d row is 3d. 4d is here, starting with atomic number 39 and going to 48. You see the M sub L values that are possible and the M sub S values that are possible. So there's there's 10 elements representing 10 electrons in the 4D. So all 10 of those sets of quantum numbers in 4D will have primary quantum numbers of n equal 4. If they're in the D block, they're going to always all have values L equal to 2. And M sub Ls will have 5 different values ranging from -2 to +2. Each of those 5 M sub Ls can have a plus or minus 1/2. So we'll have a total of 2, 4, 6, 8, 10. 10 sets of quantum numbers that you would expect in the 4D energy orbital range.